Hi there and welcome. Today I'll show you how to build this speech-to-text voice recognition application using Python and the Vosk language models. The application can recognize speech for multiple languages and it can process multi-language voice commands. It's a useful tool for everyday dictation and extremely useful to send text prompts to your private chat application. Use it as a standalone voice recognition application or integrate it into your own projects. Let's get started. Stop. This is a Python-based application that uses Flask for the server-side logic and data exchange between the back-end and front-end. Flask is extremely useful for maximum control of the front-end and for requesting data without having to refresh the browser or restart the Python app. Vosk is an open-source speech-to-text library that provides speech recognition capabilities. Vosk converts sound waves to text. PY audio is used to record audio from the microphone. Firstly, we'll set up the Python environment and install the Python requirements for the project. Next, we'll create the project folder and file structure. Then we'll download some Vosk language models. We'll start copying over code, and with each step, we'll test the app in the browser. We'll be inserting code to 4 files: app.py, INDEX.HTML, MIC.JS and MIC.CSS. After the initial testing of the code, I'll explain it in a purpose-built code presenter. The source code is available from my website clemtech.xyz in the post Vosk speech-to-text standalone. I'll be referring to this post to copy over code. I'm developing on an Intel i7 machine with 32GB of RAM and 12GB of GPU running Windows 11 Pro. I'm using Python version 3.11. Use this version or later for your project. I'm using PowerShell for my command line utility and the Google Chrome browser with English and Italian dictionaries installed and cache disabled. I'm using Visual Studio Code for my code editor with indentation set to 4 spaces and character encoding set to UTF-8. For voice recognition, at minimum, an inexpensive podcast mic will enhance your speech recognition and produce reasonable results. Let's go ahead and create the Python environment. Start with a project folder. I'm naming my project folder Vosk. Using PowerShell, create the folder. Next, create the Python environment. And finally, activate the environment. Installing the Python requirements. Before we start, let's see what Python libraries we have, so later we can tell which additional support libraries get installed using the command piplist. Let's go ahead and install Flask, Flask WTF and requests. Let's inspect the library versions. These are the latest builds and we'll be proceeding with these. Install Vosk and PY audio, then check the versions. Let's create the project structure. Create the following folders. Let's create a working folder called user data. And note, the folders static and templates are required specifically by Flask. Flask searches for an index.html file in the templates folder. Create the files to house the code: app.py, MIC.JS, MIC.CSS and index.html. And finally, create the folder used to house the language models. Let's download some Vosk language models from alphacify.com. Use a link from my website. For now, stick to small language models and then later you can experiment with larger ones. I'm downloading small models for English and Italian, and these are licensed under Apache 2.0. Once downloaded, unzip the files and move them to the STT models folder. Ensure that the models folder structure looks like mine. Let's add code to app.py. Copy the code from my website and paste it into app.py. Notice at the bottom of the file, this code starts the web server and launches the Flask development server. In a moment, we'll run the app and inspect the code, but before that, change the app version and modify the Vosk language model list to only include the models that you downloaded earlier. Save the file once you've made the changes. In PowerShell, have your Python environment activated and ready. Next, we'll run app.py and check for errors. Run the app using the following command, but also ensuring that you use your version of Python and project file path. There are no errors with the code so far. Errors at this stage will likely be due to missing libraries or incorrect indentation. Later you'll be visiting this URL in your browser, but right now there is nothing to see. Let's move away from the code editor and into the code presentation. These are the libraries and dependencies for the project. These are the Flask libraries and dependencies. Flask and render template are used to render data to the browser. Request provides access to incoming HTTP request data from a client. JSONify handles serialization. These are used for Flask forms. These are the Vosk libraries and dependencies. Model is used to load language-specific models, and Caldi Recognizer serves as a core component that manages audio input processing and generates transcription results. PyAudio is used to record audio from the microphone. This creates the Flask instance and sets up a private key for the application. This function returns a list of Vosk language models used to populate a Flask select field. This sets up a Flask form in preparation to render data to the browser, where it is processed in the INDEX.HTML file. The form contains a select field containing the Vosk language models. This is the Flask route to the root of the website. This index function is mapped to the root of the website. Here we're rendering the app version and form data to the file index.html, where it will become accessible for processing by Ginger2 and JavaScript. This is the main Python function. This sets up the Flask route for MIC that maps to the function MIC for processing post requests. Now that we arrived at the main Python function, let's take a look at the overall process flow of the app. Here's the first process flow that produces a JavaScript error if by chance there is no data to process. The expected data is the action and the language model. In this second process flow, there is data to process and the MIC function waits for speech from the microphone. Once it picks up speech, this marks the start of the audio chunk. Now the function waits until there is silence and this marks the end of the audio chunk, and the mic stops listening. With the audio chunk in hand, the audio is converted to text and sent to the front end. Each text chunk is appended to the text area, and it is also added to a text history array. Then the mic listening process starts again. In this third process flow, audio has been converted to text and is sent to the front end for processing. A check is made against the possible voice commands. These are single words: back, send, and stop. If the voice command back is returned, the last entry of the text chunk history array is deleted, and it is also removed from the text area. The mic process starts again. If the voice command send is returned, recognition of the command is sent to the console. This is where you would code where to send the text, like to a chatbot. The mic listening process starts again. If the voice command stop is returned, including if the stop button was clicked, this stops the process entirely and can only be started again by clicking the start button. Here we receive data from the front end and we expect some data. If we have data, this is assigned to variables user message and user options. User message does not hold any data in this project. I keep it alongside user options as a matching pair for all my asynchronous functions. Here we assign values from user options to variables. Action will only ever hold the value start. We extract a value for the Vosk language model. Here we set the language model directory path and assign it to the variable model path. Here we load the language model and assign it to the variable model. This code initializes a speech recognition object with a specific model and audio sample rate. In our case, a sample rate of 16 kHz, which is suitable for high-quality voice applications. This instantiates PyAudio. This opens an audio stream with the following characteristics. Here we specify the audio format as 16-bit signed integers. This is the standard format for audio processing, offering a balance of quality and file size. Configures the audio input for a single channel. Sets the sampling rate to 16 kHz. This sample rate is common for speech processing applications. This designates a stream direction as input, indicating that data will be captured from a microphone or from another input device. This defines a number of frames read at a time into the audio buffer. This is the point where the mic begins to capture sound, in our case, speech. Clear text is used to store the converted text. Here we set it to an empty string. This while loop keeps the script running while the audio stream is active. The stream remains active until the clear text variable holds some real text. Here we read data from the audio stream. 4096 specifies the maximum number of bytes, or frames/chunks, to read and return in this single operation. This condition returns true when the recognizer processes enough audio data to detect a complete spoken phrase. Then the recognizer retrieves the finalized JSON text transcription of the spoken phrase. Here we strip out unwanted characters from the JSON text before sending it to the front end. Here's an example of the retrieved JSON text and the text the way we want it. We break out of the while loop when clear text holds real text. My mic picks up noise that transcribes to HUH when left listening unattended. This conditional statement checks for this text and discards it if detected, resulting in the listening process to continue. Remove this extra bit of code if your mic doesn't pick up the unwanted noise. Once we're out of the while loop, we stop and close the audio stream, and we shut down the PY audio interface. Here we return the JSON response to the front end. The response will contain the cleaned text. In the case of errors, these are returned as a JSON response to the front end. For example, an error will occur if invalid data is sent from the front end. That concludes the code presentation for app.py. Let's add code to index.html. Copy the code from my website and paste it into index.html, then save the file. In a moment we'll inspect the code, but first let's run the app in the browser. Check that you have app.py running in PowerShell. Have your favourite browser ready and enter the URL http://127.0.0.1:5003. We'll add the styling a little later, but hopefully you see something similar in your browser. Let's move away from the code editor and into the code presentation for index.html. We use Ginger2 syntax to extract the version data. Here we include MIC.JS and MIC.CSS into our project. Both of these files are currently empty. We use Ginger2 syntax to extract data for the label and languages select field. These are the hard-coded buttons. This code builds the mic status section. This is where our transcribed text will be displayed. That concludes the code for index.html. Let's add the CSS styles. Copy the code from my website and paste it into MIC.CSS, then save the file. These are the style definitions for the mic status spinner. You can change the spinner's color here. Let's run the app in the browser. There's no functionality right now, but hopefully you see something similar in your browser. Let's add the JavaScript code. This is the last of the code and it will give life to the app. Copy the code from my website and paste it into MIC.JS, then save the file. In a moment we'll run the app in the browser and then inspect the code, but first check that app.py is running in PowerShell. Also bring up the browser's developer tools to check for JavaScript errors. Press F12 or Ctrl+Shift+I on your keyboard to bring up the tools and select the console tab. This is the moment you've been working towards. Go ahead and refresh the browser. There are no errors. Now for the test. In summary, we entered code into 4 files and now we are live testing. Testing 1, 2, 3. If you want to clear the last transcribed text, you say back. This is a mistake. Back. If you want to send the transcribed text somewhere, you say send. Watch the developer console when I say send. Send. To stop the app, you say stop. Stop. Oggi è un ottimo giorno per scrivere. Ciao. Manda. Ferma. And there you have it. Transcription accuracy appears to be around 90%, maybe higher. A chatbot can make the grammar and spelling corrections with ease. Next, we'll take a look at the JavaScript code. Let's begin the code presentation for MIC.JS. Here we declare a global variable to hold the MIC action, or if you like, the MIC's state. Here we declare a global array to hold the transcribed text history. It's used with the voice command back, whereby the last text entered into the text box is deleted. This is the asynchronous function for the project's front end. The function is initially triggered by the click of the start button. Here we store multi-language voice commands in a two-dimensional array. English and Italian voice commands are included here. We declare and set a variable for the language mode. The language mode is used together with the language voice command array. Here we set the language mode given the selected language retrieved from the languages drop-down box. Here we get a reference to the text area used to display the transcribed text. We make a call to the function setMicStatusView, which starts the spinner animation. Here we assign data to send to the Flask MIC route in app.py. This is how app.py receives the data. This code sends an asynchronous request to the Flask MIC route in app.py and waits for a response. The expected response is transcribed text, either a complete phrase or words from the voice commands. A message and options data is sent along with the request. While the message data remains empty, the options data contains the button action and the selected Vosk language model. Here we parse the JSON response from the backend, and here we process the return data from the backend. This condition is true if the start button was clicked and remains true until the stop button is clicked or the voice command stop is detected. With each response from the server, a new request to listen is sent back, and the process continues until a stop has been detected. The code on lines 62, 71, 77 and 87 have been commented out but left in the project. The code shows an English-only implementation of voice commands. The code was left so that you can easily see which voice command we are checking for. If this condition is true, we process regular text. Here we append the return text to the end of the text area. Here we add the text as an item to the end of the MIC history array. And here we make the call to send MIC action, which starts a listening process again. If this condition is true, we process the multi-language voice command for stop or the stop action from clicking the button. Here we set the MIC status, and here we set MIC action to stopped. From this point, we are no longer accepting audio from the microphone. If this condition is true, we process the multi-language voice command for send. If you integrate this project into a chat application, you would send the return text to the chatbot here. In this project, we send the message to the console. And here we make a call to send MIC action, which starts the listening process again. If this condition is true, we process the multi-language voice command for back. Provided that there are items in the history array, we remove the last item from the array. And then we rebuild the text for the text area from the items in the history array and assign it to the variable new text. Then we assign the new text to the text area. Then finally, we make a call to send MIC action, which starts the listening process again. This is where the asynchronous request handles any errors. The MIC status is updated if an error occurs. The function doMIC_options processes the MIC options coming from the buttons start and stop. If the stop button was clicked, we check if the MIC action is something other than stopped. If it is, we set the MIC status to stopping. Continuing on from the first condition, we set the MIC action to stop. Then we exit the function. If we reach here, the start button was clicked. Here we get a reference to the text area used for the text output and later give the text area the focus. We set the MIC action to listen and we make a call to send MIC action, which triggers the start of the listening process. The function setMIC_status_view sets the MIC status text and spinner animation. This function returns a selected value from the language's selection box. That concludes the code presentation for MIC.JS. This brings us to the end of the presentation. I hope that you had success implementing the speech-to-text app, and I hope that you find it useful to build on top of. I plan to create more project-based videos like this one. If you like this video, please let me know in the comments. Also, I would appreciate the thumbs up. See you next time.